Okay, we're going to start our study by looking at simple structures with cables. So as an example, consider this suspension footbridge here across a rocky canyon. So we have a few cables holding it up. Now it's not a very large span and it doesn't have to hold a very great load, so we just have a few cables that can hold this thing up. And the questions we're going to want to ask is for a known load in this bridge here, and as people walk across it, what are the tensions in the cables and how big do the cables need to be to support those loads? So most of the examples that we're going to do here are demonstrations with string. So string will be our cable, and it has the same properties, right? Which is a string can be compressed, it can't be bent, it can only support a load and tension. Now the string is going to exert a force, and force, as you probably know, is represented as a vector. So a vector is nothing more than an arrow that has a magnitude and a direction. So the length of the direction, the length of the arrow denotes how strong the force is, and the direction the arrow points is nothing more than the direction the force points. So when we talk about the force on my hand here on the left exerted by the string, with the string, the force and the structure itself of the string have to be aligned because the string can only pull. So the force is in the direction of the string, and the length of the arrow represents the force. Now, in this structure, we're going to need to go to each of these nodes and analyze what each cable or string is doing. So the device that we're going to use is called a free body diagram. And here's an example where I have 3 strings pulling on a washer. And the free body diagram is going to denote the forces that are acting on the washer. And for the washer or the joint here to be in equilibrium, right, the forces are going to have to be in balance. If I pull too hard to the right, the whole thing wants to move. So the sum of the forces is going to have to equal to 0 in order for this washer to be at equilibrium. So let's draw the free body diagram of the washer. So all that means is we draw just the washer as though it's the only thing in the world that exists, hence it's a free body. And then we're going to draw the forces that are acting on that body. So we have a force here for F1, which is the force due to string 2, a force here due to string 2, and a force here due to string 3. And if we look carefully at the direction of the string, we'll find that they all pass or pointing right at the center of this circle. So an important thing about the force is that the line of action all will intersect right here at the point. And our free body diagram is going to be the device that we use to represent the forces, and then for the device to be in equilibrium, or in this case the washer, the forces pulling upwards need to balance the forces pulling downwards, and the forces pulling left and right need to be in balance, otherwise the object's going to move. Now in order for us to be a little bit more quantitative, we're going to build a lot of little simple structures here in our demonstrations with string and fishing weights. So we have a little fishing weight here, which is going to be our load, which is going to be known, right? We know the weight of this little bobber. And what we're going to do is we're going to hang our structures on the wall, and then we're going to ask the question, what's the tension in these 2 strings needed to hold this weight up? And now this will be a convenient experiment because we can do the following thing, which is I can tape this to the wall, I can take a picture of it, and then I can print it, which is what I've done here. And now that gives us something that we can draw on to analyze. So we have 3 forces that are acting. We have the known load, which is our fishing weight, acting downward. So in mechanics, we always call the known load P. We have the tension in this string pulling this direction, so I'll call that T1. We have the tension in this string pulling in that direction, I'll call T2. And that is our free body diagram for the node right here, where these 3 strings intersect, so the knot or the washer. So we have those forces and those forces, and what we want to do is figure out what the magnitude of T1 and T2 are, given that P is known. So the first thing we're going to do here is draw a coordinate system. So there's my x direction, there's my y direction. And then we're going to break our vectors T1 and T2 into x and y components. So we're going to have a vertical component here in the y direction that I'll call T1y. And we're going to have a horizontal component here that I'm going to call T1x. And then likewise over here, we have the same thing. We have T2x and T2y. Now the next thing I need to know to find the magnitudes of T1 and T2 is I need to know what the angle is here. So I can use my little protractor here and I can measure the angle, except in this case I don't have to because I built this so I know exactly what the angle is. And conveniently I made this angle here 45 degrees, this angle here 30 degrees, though of course this could be anything we want. Okay. So now we have to sum the forces in the x and the y direction and then set those equal to 0 in order for our node here, or our knot, to be at equilibrium. So I'm going to write a simple equation here. I'm going to sum the forces in the x direction and I'm going to set that equal to 0. And in this case there's only two x forces, T1x pulling to the right, T2x pulling to the left. So an equivalent statement is that T1x needs to equal T2x. And in this case, finding T1x in terms of the note of the tension in the string is just given by geometry. So simply T1 times the cosine of 45 degrees equals T2 times the cosine of 30 degrees. Now you might remember your sines and cosines and that these numbers come out nice and evenly. So the cosine of 45 degrees is 1 over the square root of 2. Cosine of 30 degrees is square root of 3 over 2. So I combine that together and you can confirm that I got this right. I get that T1 and T2 are related through this expression. So it doesn't tell me what T1 or T2 are, but it tells me how they relate. Now let's go and sum the forces in the y direction. So we're going to do the same thing. We're going to write that the sum of the forces in the y direction equals to 0. And in this case, I have three forces. So I have the known load P from the fishing weight pulling down, and then I have T1y and T2y pulling up. So I'll say that my downward force P is equal to T1y plus T2y. And again, we know that T1y is nothing more than T1 times the sine of 45 degrees plus T2 times the sine of 30 degrees. And now again, I know that the sine of 45 degrees is also the same as the cosine, 1 over the square root of 2. The sine of 30 degrees is a half. So I can take these two relationships, I can combine them. Namely, I can stuff in my relationship for T1, and then I can solve for what T1 and T2 are in terms of P. So putting in actual numbers, instead of writing the square roots, I get that T2 is equal to 0.732 times P, and T1 is 0.896 times P. So now I know what T1 and T2 are in terms of my known load P. Now let's look at a slightly different way to do the think about these forces geometrically. So let's just start with a clean sheet here, and let's remember our result. That T1 is equal to 0.896 P, and T2 is 0.732 P. Now I'm going to draw my vectors a little bit more precisely. So I'm going to take my ruler here and I'm going to mark my vector P, and just for the purposes of this video I'm going to make it 2 inches so it shows up nice. So I'm going to put the point of that right at 2 inches as best I can, so 2 inches from there to there. Now I'm going to draw my vectors T1 and T2, but I'm going to draw them as best I can to proportion. So T1 would fall about there, and T2 is going to fall right about there. So now those vectors are drawn to proportion. But there's a relationship here that's maybe a little bit hard to see when the vectors are drawn this way, which is another statement to say that the vector sum needs to equal to 0, means that if I take these vectors and I move them around and I arrange them tail to tip, so that they'll have to form a closed triangle. And so we can see that a little more easily if I use my sliding ruler. So what I'm going to do is I'm going to take this string here and I'm going to extend it, and I'm going to take this string here and I'm going to take the same angle of that string, but I'm going to use my sliding ruler here come down here and draw a line that intersects like that. And so what that means is this vector here needs to be T2, and this vector here needs to be T1. Now I can take my measurement and I can confirm that this vector here is a little bit under 1.5 inches, meaning that when my load is P is 2 inches, then I have this relationship here. And I can also take and confirm that the length of vector T1 is about 0.9 of P. Now of course if I measure accurately and I draw accurately, I can get this really almost as good as I want. And another way we can see that T2 is correct is I can come here, and if I draw kind of a dotted line here, I can see that they intersect at the same point. So that hopefully that kind of shows that all I've done is I've taken this vector here and I've slid it down here, I've taken this vector and I've slid it back here to show that the vector sum equaling 0 is nothing more than the 3 vectors have to make a triangle. Now this way of solving for the forces or the tensions in the lines I can do without using any equations, because you can see I drew that construct by extending this line, taking this vector, moving it here, and then simply measuring the magnitude of the vectors. It allowed me to get this relationship, maybe not quite as accurately as doing it mathematically, but really, really good. And you have to remember that when we analyze structures, we often don't care about this level of precision. So the accuracy that we can get from this graphical technique is really quite good and good enough for the purposes that we'll need. So this is kind of a trivial example, so in the subsequent videos we'll analyze more and more complicated structures.